Hello, welcome everybody. This is Fabrizio Silvestri. I'm currently a research scientist manager at Facebook AI, supporting a team of people working on applying artificial intelligence techniques and developing new artificial intelligence techniques to fight integrity-related issues on Facebook. Integrity-related are, issues that prevent a good user experience for our users, for our people. The subject of this presentation is actually one of the things that have been done by me and my team in order to improve the quality of the classifiers that we have, the text classifiers that we have, when we are in presence of misspellings. And as we will see, misspellings can also be actually maliciously injected by people. So let's start it. I think people, following this talk don't really require a comprehensive introduction to neural networks, but what I would like you to kind of mind is the fact that in most of the cases, even in the case of textual classifiers, the input to a neural network is a set of numbers. Even if you want to input text, you first have to transform that text into a list of numbers. And of course, there are several ways of doing it. Possibly the most straightforward way is to consider the vocabulary of all the possible words in your text and to assign a number, let's say an ordinal number, to each of the words of the token in the vocabulary, and then to represent those words as the one hot encoding representation of the word, which basically means a bit vector of size n, where n is the number of words you have in your vocabulary, where you set only one bit to one corresponding to the position of the, let's say, the word in the vocabulary. Now, this, as you can imagine, is inefficient, and therefore, in the last, I would say, few years, better ways of representing words have been, let's say, designed. Probably one of the most famous is that of word embeddings. And basically, the idea is very, very simple, and it's summarized in that saying by Firth in 57, "You shall know a word by the company it keeps," which basically means that the context within which a word appears is very important to understand the meaning of a word and to kind of understand what a word means. Just to give an example, if I present you a sentence and I remove a word, it's pretty straightforward in most of the cases to fill in the blank. So for our purpose, let's consider a vocabulary D, in this case, of some words, Bob, cat, dog, fly, zen, in this example. And now the goal is that we want to actually assign a number, V, to each one of the words in the vocabulary. Now, when I say a number here, I don't necessarily mean a single real number. A number can also be a vector in a vector space. The only constraint that I have is that this number, this vector, should encode some information about the word itself. For instance, one of the most intuitive things that you want to encode using a vector space representation for a word is that two words that are similar in their semantic meaning should be also close in the vector space. Close could be like the angle between these two vectors should be small, or the dot product, which is correlated to the angle. So once you have that, for instance, in this example, we encode the word cat with 0.3, 11.4, 1.9, you can then feed these list of numbers to a neural network, and then you can train a neural network. Now, if you have multiple words, such as in a sentence, you have to devise different architectures, but eventually it all boils down to first encoding each word in the text via these embeddings, and then feed those embeddings to the neural network architecture. Embeddings have pros and cons. For instance, as I said, inputs also encode semantics. So the encoded version of cat is closer to the encoded version of dog than that to Bob. And these can already be useful. For instance, you can run clustering algorithms on the vectors you have built, and you will end up with clusters of similar words. There are plenty of examples in the web if you want to have a look at that. Also, the dimension of the input space is independent on the size of the vocabulary. And as I said before, the one hot representation is of size D, where D is the number of words in the vocabulary. And usually the size of the vocabulary is in the order of hundreds of thousands or even millions, million of tokens. And whereas M, the size of the vector space, is usually in the order of hundreds. I mean, 512 or even less. But of course, this comes at a cost, and the cost is that of training those embeddings. So you cannot just assign an ID and then flip a bit in a bit vector. You have actually to train these embeddings. And this is actually the subject of papers that have been produced in the past, I would say, 10 years. In particular, maybe one of the most famous word embedding is word2vec, developed by Thomas Mikolov and other people in 2013, while Thomas was at Google. Basically, the idea is very, very simple. As I said at the beginning, you consider a sentence, you take out a word, and then you try to predict that word. And how you do it? But well, you feed as an input all the words in the sentence, and then you want to obtain as the output the hidden word. So this architecture that you can see here is exactly representing that idea. You have the one-hot encoding of the input, and you project via a matrix that one-hot vector, say bit vector, into a lower dimensional vector space, in this case dimension D, and then you take this lower dimensional vector and you reconstruct the word that in the example that I was making before, it's the missing word. So the input and the output is different. It's very, very similar to what an autoencoder does, but differently from autoencoders. Here you want to reconstruct a different output, which is, in this case, the context that you want to reconstruct. So basically what you end up with, say, let's say, vectors that are representing the words. Now, one of the issues of Word2Vec, well, first of all, one of the pros of Word2Vec is that it's extremely fast. It's embarrassingly fast to train. I guess that one of the most important reasons why Word2Vec was successful is that it was extremely fast to train. And and in particular, if you compare, let's say, the training phase of nowadays language models that require weeks on supercomputers with GPUs, you will notice immediately that Word2Vec is extremely faster than those, because it can be trained on a laptop in a matter of minutes or hours at maximum on a like relatively large corpus, because it's basically linear in the size of the text. I will not delve into details of how the training is done. You can go and read the paper. But one of the issues with Word2Vec instead is that it cannot handle cases where you have not seen the word in the during training or out of vocabulary words. So the idea of a follow-up work done by people at Facebook AI, Bojanowski et al., is that of considering the set of n-grams making up a word. And this way, you basically go and learn how to compose the representations of those n-grams to form the representation of a word. So why is this better? Because n-grams are finite in numbers. So basically, you have, if you consider like bigrams, trigrams, fourgrams, you only have a finite number of um, elements in the set of n-grams. So you considerably reduce the search space, the vocabulary space, and then you learn how to compose the representations of those n-grams as well. There is also another advantage of this approach, which is the fact that you also learn how to appropriately consider morphological variations of words. So late, later, latest, those are all variations of the word late. And FastText that is trained on n-grams, subwords, basically is able to consider also morphological variations appropriately. Now, this idea is represented in the slide, in the diagram that in the picture in the slide. So basically, if you have the word bird, you compose in this case the representation of the word bird by averaging the representations of the word BIR and IRD, right? So this is a very important step that we considered also in our work. But let's see what are the. So first of all, okay, what are the pros? As I said, it handles out of vocabulary words. It is extremely fast. It is as fast as Word2Vec. It has only, of course, a multiplicative factor that is depending on the number of n-grams per word, but it's really negligible with the training data. But there is an issue. The real issue is that if you have a misspelling in a word, then the whole, also, let's say, the whole averaging method that you use to obtain the final representation is basically useless. Like if you look at the example here, by only changing one character, you change the whole representation of a word. And this, of course, is especially true for short words. So this was, let's say, the observation that we made when we came up with the idea of misspelling oblivious embedding. There was also a real motivation driving this work. And basically, the motivation came from a problem that the search team at Facebook had. So basically, the search team wanted to classify offensive queries. But the problem is that offensive queries are prone to adversarial modifications. So if you have an offensive term, you can see some examples in the slide, people started to modify the terms in a way that humans could read easily, but machines couldn't understand that those were offensive queries, offensive words. So they were passing our classifiers, and unfortunately, for those queries, we were also generating suggestions, we were generating results. So we didn't want those, say, queries and those tokens to appear in our search results. So we came up with the idea of making our embeddings resilient to misspellings. Sorry, I forgot to mention that another thing is that our search system, in general, search system, has to operate in a very timely fashion. So you have to answer a query in a sub-second with a sub-second latency. And also, the query classifier was run before all the other things. So you cannot really take too much time. And so more modern classification schemes were ruled out because we couldn't use, for instance, a BERT or a contextual embedding based technology because it was too expensive. So we came up with this idea, Misspelling Oblivious Embeddings, that we published at NACL in 2019, last year. NACL is one of the top conferences in natural language processing. And the idea is quite, I would say, straightforward, but then the implementation is not so straightforward. Basically, the intuition is the following. If I could feed together with a word all of the possible misspellings or lots of possible misspellings for that word, can we learn to basically detect patterns of misspellings for those words and use those patterns to basically correct while embedding those misspellings? So the intuition here is the following. Once you have trained your vector representations for words, misspellings should have a representation in the vector space that is close to the original word. So what we did was exactly that. We added to the FastText method, the FastText training, a component, a sort of additional task that is a supervised task that consists in learning how to correctly represent a misspellings close to the original word. So now, as you can imagine, we are optimizing for two different objectives. One is that of basically putting closer together semantically similar tokens. And the other one is to put closer together misspellings with the original word. And of course, these two things have to be done in conjunction. And this is the idea. So this idea was actually pretty successful, both internally and externally. For instance, externally, we had blog post in the Facebook AI blog that received a lot of attention. I mean, lots of people picked up on the idea and they analyzed it. And as far as we know, there are also other companies that are using these. And internally as well, the classifier that I showed you before was improved very substantially using these misspelling oblivious embeddings. I promise this is the only slide with formulas, but I wanted to give you the flavor of, let's say, in practice, what changes with respect to FastText. So you can totally see that the loss that we are optimizing is a combination of two losses. One is LFT, which is the FastText loss, nothing changed. And the other one is the MOE loss, the misspelling oblivious loss, which, if you look at the slide, it basically consists in maximizing the log likelihood of, let's say, the probability of, let's say, correctly associating the correct word with a misspelling. Where those misspellings are coming from, they're coming from a corpus of misspellings that in this case we mined from our search queries. So now the intuition is the following. The goal is to make the n-grams of the misspelled words actually aligned also with the n-grams of the non-misspelled words. And this is the basic idea. So let's see at some experiments. So first of all, let's see what is the setting within which we operate. We have a training data set, and we trained the semantic loss using Wikipedia as FastText and Misspelling Oblivious Embeddings. And for the spell correction loss, we generated a training data set from our search queries. Now, I'm actually very pleased to say that this data set is publicly available, and it contains a huge number of misspelling pairs. It's actually, at least to date, is the largest misspelling corpus. So this actually can be used to develop better, for instance, spell correction, spell checking technologies. And as I said, misspellings are actually generated via a real error model that was trained on Facebook search queries. So the misspellings that you see are not actual misspellings copied from our logs, but they are misspellings that are very, very likely to appear in our log. I mean, the difference is subtle, but is very important. So we are not releasing any user information here. We are generating things. So we don't know if those misspellings were actually present in our logs, but the likelihood is pretty high. So we run some experiments. The first one, the word similarity experiment, is a typical intrinsic experiment, intrinsic task that you run when you want to verify the quality of embeddings. And basically what you do is, you given pairs of words, pairs of similar words, you want to see if the distance between the similar words is small, right? So here in the plot that you can see, we actually varied the importance. We actually varied two things. First, we varied the amount of misspellings we introduced in the dataset. So when R is equal to 0, the green line, it means that the dataset is not perturbed and we don't inject any datasets. It's a clean dataset. As R increases, so the 4 lines, the 3 lines that you see there, the number of misspellings increases as well. And as you can see, there is also another parameter here, it's alpha. Alpha, it's basically, if I go back to the previous slide, it's basically the parameter governing the importance you give to the misspelling oblivion component of the loss. So as alpha increases, you give more importance to misspellings in the training. So for alpha equal to 0, it's basically the same as FastText. And as you increase alpha, you have more and more importance to misspelling oblivious embeddings. And no surprises there. If, let's say, you increase the number of misspellings, by increasing alpha, you actually increase the quality of the embeddings. So this is a first, let's say, check, that we wanted to make in order to validate the hypothesis that our embeddings were more robust than misspelling. So in this case, for the word similarity task, it was. We did another task that consisted in understanding whether when you go and you retrieve for each word the top k most similar words in your vector space, you wanted to check whether those words were, let's say, the correct word or not. So basically the idea is that you take a word, you misspell it, and then you retrieve the top k similar words in the vector space to the misspelled word, and you want to see if the correct version of that word appears in the top k neighbors. So we tested for k from 5 to 100, k equal to 5, 10, 50, and 100, and again for different values of alpha. And again, no surprises here. The quality, the number of times you actually find the correct word in the neighborhood increases with increasing alpha. So if you give more importance to misspellings, you actually retrieve. It's more likely that you retrieve the correct spelling, except if you consider alpha equal to 1, where you can see a decrease in the quality, which is possibly due to the fact that you are really overfitting over your training data. So it's a sort of a generalization issue here. Then the last test that we ran is that on an extrinsic task, in this case, part of speech tagging. That is, we used our embeddings in a real world task, in this case, part of speech. So given a sentence, you want to tag each of the tokens in the sentence with the appropriate part of speech, like nouns, verbs, and so on and so forth. And again, we did the following setup. First, original training data and original test data, which means no misspellings at all. And then we misspelled 10% and 100% of the training data, meaning all of the tokens in the case of the 100% and 10% of the tokens in the case of the 10%. And then we also misspelled all the test data, or we didn't misspell any of the test data. And we wanted to check whether we could actually measure some impact on our misspelling oblivious embeddings. And as you can imagine, yes, we can see a huge impact when we have a lot of misspellings. So in the case of 100 misspelled training data, 100 misspelled test data, when alpha is equal to 0.05, we actually see the biggest improvement, almost 2%, in the case of, let's say, F1 score for the part of speech tagging. But also, more interestingly, in the case of original, we see that the misspelling oblivious embeddings for alpha equal to 0.01 is better than FastText, and it's statistically significantly better than FastText. And this is surprisingly, and we think that the reason why it is better than FastText is because adding misspellings, it adds a sort of regularization factor, right? So it improves the generalization performance of the model. So basically, this is it. What we have presented in this work is a new kind of word embeddings that are resilient to misspellings. Word embeddings are very, very important because they are ubiquitous in NLP. Basically, word embeddings are now, I mean, you cannot do NLP without word embeddings. If you have followed the GPT-3 fuss of the last weeks, you know what I'm talking about. Basically, with word embeddings, you can generate text, you can generate all kinds of stuff, and they're almost magical, almost surprising. But in general, embeddings are not resilient to misspellings, and this is what we try to do. Note that the technique that you see here is actually applicable to all of the embeddings, including contextual embeddings, because it's a modification of the loss that depends on the supervised training dataset containing misspellings. And in fact, this is one of the things that are worth being investigated in the future. And let's say this is it. I hope you took some message away. As I said, and in my opinion, the main takeaway of this presentation should be that you can actually make embeddings more resilient to misspellings by training, let's say, the directly a loss with misspellings associated with each word. And another takeaway that I would like you to let's say, get from this presentation is that you can actually make also these embeddings more resilient to adversarial misspellings by, again, by adversarially modifying words and apply the same training mechanism, in that case. So we actually solved both of the problems at once. And again, with that, I'd like to thank you all for listening to my presentation, and I hope you will find this work helpful also for your technologies. Thank you.